Q6210. Which condition could be expected if a strong temperature inversion exists near the surface? A. Strong, steady downdrafts and an increase in OAT. B. A wind shear with the possibility of a sudden loss of airspeed. C. An OAT increases or decrease with a constant wind condition. The correct answer is B. When a strong temperature inversion exists near the surface, it can create conditions that lead to a wind shear and the possibility of a sudden loss of airspeed. Let's explore this further. A temperature inversion refers to a layer in the atmosphere where the temperature increases with height, contrary to the usual decrease in temperature with altitude. Inversions can occur for various reasons, such as radiational cooling of the surface at night or the presence of warm air aloft. In the context of aviation, a strong temperature inversion near the surface can create a stable layer of air that acts as a barrier to vertical mixing. This means that the air in the lower atmosphere, including the boundary layer close to the surface, may have different characteristics compared to the air above the inversion. In this scenario, wind shear becomes a concern. Wind shear refers to a rapid change in wind direction or speed over a relatively short distance. When a strong temperature inversion is present, it can create a sharp contrast in wind conditions between the lower atmospheric layer and the layer above the inversion. Typically, surface winds within the inversion layer are relatively light and variable. However, above the inversion, stronger winds may exist. The presence of this wind shear, with a significant difference in wind speed and/or direction between the two layers, can pose challenges for aircraft. When an aircraft encounters this wind shear, it may experience a sudden change in airspeed. The abrupt transition from the lower atmospheric layer with light and variable winds to the layer above the inversion with stronger winds can lead to a sudden loss of airspeed or a significant variation in airspeed. This can affect the aircraft's performance, stability, and control responsiveness. Pilots need to be aware of the potential wind shear associated with a strong temperature inversion near the surface. They should consult weather information, such as terminal aerodrome forecasts, TAFs, and meteorological reports, METRs, to identify the presence of inversions and wind shear alerts. Additionally, wind shear detection systems installed on some aircraft can provide real-time information about wind shear conditions. In summary, when a strong temperature inversion exists near the surface, a wind shear with the possibility of a sudden loss of airspeed can be expected. This highlights the importance for pilots to remain vigilant, be prepared for potential changes in wind conditions, and take appropriate measures to ensure the safety of their flights. 6313. What is the expected duration of an individual microburst? A. One microburst may continue for as long as an hour. B. 5 minutes with maximum winds lasting approximately 2 to 4 minutes. C. Seldom longer than 15 minutes from the time the burst strikes the ground until dissipation. The correct answer is C. Microbursts are intense, localized downdrafts of air that can occur during thunderstorms and pose significant hazards to aviation. Understanding the duration of a microburst is crucial for pilots and air traffic controllers to assess the associated risks. Here's a closer look at the expected duration of an individual microburst. Microbursts typically have a relatively short duration, seldom lasting longer than 15 minutes from the time the burst strikes the ground until it dissipates. This means that the entire life cycle of a microburst, from its initial impact on the surface to its dissipation, is relatively brief. During the lifespan of a microburst, there are distinct phases that pilots should be aware of. The first phase is the outburst phase, where the downdraft reaches the surface and spreads out horizontally. This phase is characterized by strong, gusty winds directed downward and outward from the center of the microburst. The maximum intensity of the winds within a microburst typically occurs during the second phase, known as the mature phase. In this phase, the downdraft reaches its maximum strength, and the strongest winds are experienced. The duration of this peak intensity can vary, but it generally lasts for approximately 2 to 4 minutes. Following the mature phase, the microburst enters the final phase known as the dissipating phase. During this phase, the downdraft weakens and the winds gradually decrease in intensity. The microburst dissipates as the downdraft becomes less significant and the wind speeds return to near normal levels. It's important to note that the precise duration of a microburst can vary depending on various factors, including the size and strength of the thunderstorm, atmospheric conditions, and the characteristics of the microburst itself. While the expected duration is generally within the range of 15 minutes or less, some microbursts may dissipate more quickly. To mitigate the risks associated with microburst, pilots rely on weather information provided by meteorological sources, including terminal aerodrome forecasts, TFs, meteorological reports, METRs, and weather radar. These sources can help identify the presence of thunderstorms and provide timely updates on microburst activity, allowing pilots to adjust their flight plans and take appropriate precautions. In summary, the expected duration of an individual microburst is seldom longer than 15 minutes from the time the burst strikes the ground until it dissipates. Pilots should remain vigilant during this period and be prepared to encounter strong, gusty winds and rapidly changing weather conditions associated with microburst. 6314. Maximum downdrafts in a microburst encounter may be as strong as A. 6,000 feet per minute, B. 4,500 feet per minute, C. 1,500 feet per minute. The correct answer is A. When encountering a microburst, pilots should be aware of the potential strength of the downdrafts associated with these atmospheric phenomena. Here are more details regarding the maximum downdrafts in a microburst encounter. Microbursts are characterized by intense, localized downdrafts of air that can occur during thunderstorms. These downdrafts are powerful columns of sinking air that rapidly descend from the base of the storm toward the ground. They can pose significant hazards to aviation, particularly during takeoff and landing phases of flight. The strength of downdrafts in a microburst encounter can vary, but the maximum downdrafts can be as strong as 6,000 feet per minute. This indicates the rate at which the air is descending within the downdraft column. Such strong downdrafts can result in rapid changes in airspeed, vertical air currents, and a sudden loss of lift for aircraft flying through or near the microburst. To put this into perspective, an aircraft encountering a downdraft with a descent rate of 6,000 feet per minute would experience a rapid downward motion of approximately 100 feet per second. This can have a significant impact on the aircraft's performance, stability, and control, requiring immediate corrective action from the pilot. It's important to note that the strength of downdrafts can vary within a microburst, with different areas experiencing varying levels of intensity. The maximum downdrafts are typically encountered in the core or central portion of the microburst, where the descending air is most concentrated. To mitigate the risks associated with microburst, pilots rely on various sources of weather information and guidance, including meteorological reports, METRs, terminal aerodrome forecasts, TFs, weather radar, and air traffic control alerts. These resources provide real-time data on thunderstorm activity and microburst potential, allowing pilots to make informed decisions and take appropriate measures to avoid or safely navigate through microburst. In summary, the maximum downdrafts in a microburst encounter can be as strong as 6,000 feet per minute. Pilots should be aware of the potential for rapid and intense downward air currents associated with microburst and be prepared to respond effectively to maintain the safety of their aircraft and passengers. 6315. How long do the maximum intensity winds last in an individual microburst? A. 2 to 4 minutes. B. 5 to 10 minutes. C. 15 minutes. The correct answer is A. Microbursts are intense, localized downdrafts of air that can occur during thunderstorms and pose significant hazards to aviation. Understanding the duration of the maximum intensity winds within a microburst is crucial for pilots and air traffic controllers. Here's a closer look at how long these maximum intensity winds typically last. During the life cycle of a microburst, there are distinct phases that pilots should be aware of. The first phase is the outburst phase, where the downdraft reaches the surface and spreads out horizontally. This phase is characterized by strong, gusty winds directed downward and outward from the center of the microburst. The second phase is known as the mature phase, which is when the microburst reaches its peak intensity. During this phase, the downdraft is at its strongest, and the maximum intensity winds are experienced. These winds can be turbulent, rapidly changing in direction and speed, and pose a significant challenge to aircraft performance and control. The duration of the maximum intensity winds within a microburst is typically within the range of 2 to 4 minutes. This means that the strongest winds associated with the microburst persist for this relatively brief period. It's important to note that the exact duration can vary depending on the specific characteristics of the microburst, such as its size, strength, and atmospheric conditions. Following the mature phase, the microburst enters the final phase known as the dissipating phase. During this phase, the downdraft weakens, and the intensity of the winds gradually decreases. The microburst dissipates as the downdraft becomes less significant, and the wind speeds return to near normal levels. It's important for pilots to be prepared for the short-lived but intense nature of the maximum intensity winds in a microburst. During this period, aircraft can experience rapid changes in airspeed, vertical air currents, and turbulence. It requires skillful piloting techniques, including the use of appropriate control inputs, to safely navigate through or avoid the microburst. Pilots rely on weather information provided by meteorological sources, such as terminal aerodrome forecasts, TFs, and meteorological reports, METRs, as well as real-time updates from air traffic control to identify the presence of thunderstorms and potential microburst. This information helps them make informed decisions and take appropriate measures to mitigate the risks associated with microburst encounters. In summary, the maximum intensity winds within an individual microburst typically last for 2 to 4 minutes. Pilots must remain vigilant and employ appropriate strategies to safely navigate through these intense downdrafts and the associated turbulent conditions. 6211. Which situation would most likely result in freezing rain? A. Rain falling from air which has a temperature of more than 0 degrees C into air having a temperature of 0 degrees C or less. B. Rain falling from air which has a temperature of 0 degrees C or less into air having a temperature of more than 0 degrees C. C. Rain which has a super-cooled temperature of 0 degrees C or less falling into air having a temperature of more than 0 degrees C. The correct answer is A. Freezing rain is a weather phenomenon that happens when raindrops pass through a layer of subfreezing air near the surface and freeze upon contact with objects on the ground. This results in a coating of ice, which can create hazardous conditions for travel and infrastructure. In order for freezing rain to occur, specific temperature conditions need to be met. Answer correctly identifies the situation that is most likely to result in freezing rain. It states that freezing rain is expected when rain falls from air with a temperature above 0 degrees Celsius, 32 degrees Fahrenheit, into air with a temperature at or below 0 degrees Celsius. To better understand this, let's consider the process involved. Raindrops form when moisture in the atmosphere condenses and combines to form larger droplets. Typically, raindrops are in a liquid state as they fall from the cloud to the ground. However, if these raindrops encounter a layer of air near the surface that is at or below freezing temperature, 0 degrees Celsius, they become supercooled. When the supercooled raindrops come into contact with objects or surfaces on the ground, such as trees, roads, or power lines, they freeze on impact and create a layer of ice. This is what we refer to as freezing rain. The situation where rain falls from air with a temperature above 0 degrees Celsius into air with a temperature at or below 0 degrees Celsius. In this scenario, the raindrops remain in a liquid state as they fall through the warmer air layer, but freeze upon contact with the colder surfaces near the surface. It's important to note that freezing rain is different from sleet, where raindrops freeze completely and turn into ice pellets before reaching the ground. Freezing rain poses a greater risk because it creates a thin glaze of ice on surfaces, leading to slippery conditions and potential damage to structures. Weather forecasters closely monitor temperature profiles in the atmosphere to predict the occurrence of freezing rain. This information helps authorities issue appropriate warnings and advisories to alert the public and take necessary precautions to ensure safety during freezing rain events. In summary, freezing rain is most likely to occur when rain falls from air with a temperature above 0 degrees Celsius into air with a temperature at or below 0 degrees Celsius. This situation allows the raindrops to become supercooled and freeze upon contact with objects on the ground, resulting in the formation of a dangerous layer of ice.